So what are some common examples of resonance that we see with allylic systems? Well, if we take a 3-atom system where we can have X double bonded to Y and then Z, and the Z atom can either have a positive charge or a negative charge. It can be a radical, an anion, or a cation. What we see here is that we have movement of electron density that allows us to delocalize that charge, whether it be a carbocation, a carbanion, or a radical. If you take a look at a couple examples, we have a cyclic allylic cation, and as long as we leave the labeling X, Y, and Z the same, A and B are able to move the electron density and the carbocation around, so that the charge on Z now goes to X. If we have an acetate anion, something that we'll deal with in a later chapter, we can take the electron density on the oxygen with a negative charge and delocalize that to the oxygen in the double bond with the carbonyl. That means we can move the charge from the bottom right oxygen to the top oxygen from C to D. Here's some common examples. Benzene, which is a compound that we're going to deal with in the next few chapters, is a hybridized structure. You have 3 double bonds that are all in conjugation, so they can quickly delocalize and they can migrate throughout the structure. If we take 1,3-butadiene, we can take the electron density between carbon 1 and 2 and put that between carbon 2 and 3. Doing that forces the electron density between carbon 3 and 4 to go on to carbon 4. So we can actually get a resonance structure that induces charge for this species. So 3 resonance structures can be drawn for other conjugated dienes, 2 of which involve separation of charge. We have a third type, type 3 carbocation, type 3 cations having a positive charge adjacent to a lone pair. You can also take and move that charge. So if I have a situation where X has a lone pair and Y is a carbocation, I can take the lone pair of electrons from X and share that with Y to delocalize the charge. The overall charge is the same in both resonance structures in this case. The formal charge is going to change a little bit as we go through. The neutral X in one structure must bear a positive charge. The fourth type, the double bonds having one atom more electronegative than the other, means that I can take and move my electron density to the more electronegative atom in a shared species. Take, for example, acetone. The oxygen of acetone is more electronegative, therefore I can take and move the carbon-oxygen double bond electrons to the oxygen, giving me a carbocation and an oxygen negative. That separation of charges is one of the things that we're going to use in later chapters to indicate the reactivity of carbonyl atoms. Rule 1. Resonance structures with more bonds and fewer charges are more stable. So if we have the difference between a neutral compound and one that has charge, but we have more bonds in the neutral, we'll take the neutral. Resonance structures in which every atom has an octet are more stable. If we have a situation in which we have a carbon that is deficient in its octet, but the oxygen can, or some other heteroatom, can donate electron density, the more stable resonance structure will be the one that satisfies the octet of all the atoms. Finally, resonance structures that place a negative charge on a more electronegative atom are more stable. If we take acetone and remove a hydrogen and leave these electrons around, it is more stable to draw the resonance form in which the oxygen has the negative charge, even though we took the hydrogen away from the carbon. So how do we determine resonance structures? Here we'll see two examples of Lewis structures. For the stabilized anion CH3CO CH2-. If we look at structure A, we'll see that the sp3 hybridized carbon has a lone pair of electrons. If we look at carbon B, an sp2 hybridized carbon exists with the unhybridized p orbital forming the pi portion of the double bond. But what we also see is with compound B, the oxygen will have a negative charge. Since oxygen is more electronegative, that's why we'll pick compound B for our resonance structure. P orbitals are required for conjugation. The electron pair on the carbon atom adjacent to the C double bond O carbonyl group can only be delocalized if it has a p orbital that can overlap with two other p orbitals on adjacent atoms. The terminal carbon atom is sp2 hybridized with trigonal planar geometry in our example. There are three adjacent p orbitals that can make an anion conjugated. Therefore, the actual hybrid has more of the charge on the oxygen and more carbon-carbon double bond character than we would have originally drawn.